This lesson is on series. So basically a series is when we take the numbers from a sequence and add them up. Okay, so it's a sum. So let's go back to our football player who has two options for a contract. His first option for the 18 games is to receive $10,000 for the first game with a $10,000 raise for each game thereafter. So we said this is an arithmetic sequence because he's adding $10,000 for each game. So that's our common difference, D. But then plan number 2, and we're going to change this up a little bit, is he gets $7 for the first game and his salary doubles for each game after that. So this is a geometric sequence. And we have a common ratio, R, which is 2 because it doubles for each game. So which salary would he accept if he wants to make the most money over the course of 18 games? And you'll see that's why we changed it from 2 to 7. So if he goes with plan number 1, his first game, he'll get $10,000. His second game, he'll get $20,000. His third game, he'll get $30,000. All the way up to his 17th game, he'll get $170,000. And then his 18th game, he'll get $180,000. Okay, if we add up all of those numbers for all 18 games, okay, with our calculator, he would get $1.71 million. Oops, that's too many zeros. Okay. For plan number 2, he would get $7 first game, then 14, then 28, then 56, then 112. I just keep doubling it. 224, 448. 896, 1792, 3584, 7168. I have to keep going down here. 14336, 28672. 57,344, 114,688, 229,376. I'm running out of space. 458,752, and then the last game 917,504. Okay, if we added up all of these numbers of this geometric sequence, our sum would be $1,835,001. Okay, so we can see that given our new situation, our sum for the arithmetic sequence is pretty low compared, well, it's probably comparable, but he would make more money with the second plan. Okay, so this example is known as a finite series. Okay, since there are only 18 terms in the sum, if there were an infinite number of terms in the sum, then it would be an infinite series. Okay, therefore, a sum, or a series, excuse me, is a sum. So we can define a series as taking all of the terms a1, a2, a3, all the way to an and adding them together, where a1 is the first term, a2 is the second term, a3 is the third term, and an is the last term in a finite series. An infinite series is defined by the sequence terms all being added up, so a1 plus a2 plus a3, all the terms in between, so we'll put ellipses, a sub n, and then all the terms after that. Okay, we use the Greek letter sigma to express the sum of numbers or expressions. So, for example, if we wanted to write the sum of all the numbers, we'll call them I. And we'll let I start off as being 1 to 3. Okay, so this sigma means sum. What this is saying is we'll let I be 1, and then 2, and then 3. So our final number is 3, and we're going to add them up. So this notation here indicates just simply 1, 2, and 3. If we wanted to talk about a series in general terms, okay, any series, we would say the sum of all the terms in a sequence a sub I, where I is equal to 1 all the way to n. So this denotes the series a sub 1 plus a sub 2 plus a sub 3 plus all the way to a sub n, because we're letting I be 1 through n. Okay? The recursive I'm not on recursive yet. All right, so the infinite series, instead of n, we would say the sum of a sub I. Instead of n, we would put infinity. So I equals 1 to infinity. So this indicates a sub 1 plus a sub 2 plus a sub 3 plus dot 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 plus a sub n plus dot dot dot, right? Because it keeps going for infinity. Okay, let's look at these two sums that we have here. So how would I evaluate the sum of 2 to the ith power for I is equal to from 1 to 6? In other words, what this is saying is 2 to the ith power, where I is 1, plus 2 to the ith power, now it's 2, so 2 to the second, 2 to the third, 2 to the fourth, plus 2 to the fifth, and 2 to the sixth. Okay, I'm only going to go to 6. That's where it tells me to stop. So this is another way of saying, okay, 2 plus 4 plus 8 plus 16 plus 32 plus 64. Okay, and if I took my calculator and added those numbers up, I would get 126. Okay, so that's that sum. Let's look at the second one. All right, so we're going to say, okay, the sum of all the numbers in the sequence 1 plus I over I, where I is equal from 1 to 4. So this would be our series. 1 plus 1 over 1, where I is now 1. Now I is going to be 2. 1 plus 2 over 2. Now I is going to be 3. 1 plus 3 over 3. Now I is going to be 4. 1 plus 4 over 4. And that's where we stop, because this indicates our stopping point for I. So then this is the same thing as saying 2 over 1 plus 3 over 2 plus 4 over 3 plus 5 over 4. And if I got like terms and then added those up, or even just got a calculator, this would equal 73 over 12. Okay, so that's notation for series, and that's what we mean when we're talking about any kind of series. Okay, now let's talk about arithmetic series. This is where we add up the numbers of an arithmetic sequence. All right, so we need to come up with some kind of general formula in order to be able to calculate the sum of an arithmetic series, especially if the series is quite large. So if we've got 100 numbers in our series, we're not going to want to pull out our TI-84s and start adding up 100 numbers. We need a general formula that will help us in an arithmetic series. Okay, so a sequence where we have a D and we're adding up all of the numbers in that sequence, that will represent this sum in general. So if we're given the first term a sub 1 in an arithmetic sequence with the common difference D, okay, we're going to use S sub n to represent the sum of the first n terms. Okay, so this is what we're going to write. This is for an arithmetic sequence, remember. Our first term is a sub 1. Our second term is going to add D to a sub 1. Okay, so this is our second term. Our third term is going to add D to a sub 2, which is a sub 1 plus D. So we could say a sub 1 plus D, or a sub 1 plus 2D. And then we'll keep going down the line. Okay, let's jump to our last term. What's the last term of a finite arithmetic sequence? It's a sub n. What's the second to the last term? Well, in order to get the last term, I had to add D to the previous term. So to get to the second to the last term, I can subtract D from the last term. To get the third to the last term, I could subtract D again from the last term. Okay, so this is a pretty accurate, well, very actually accurate way of representing an arithmetic series. But it still doesn't help me come up with a general formula in order to obtain the S sub n, or the sum of a finite number of terms in the sequence, in a really concise, easy way. So why don't we take this sum, now we're going to write it in reverse, because the commutative property allows us to do that, right? All we're doing is adding up numbers. So I'm going to take the same sum, right? So it still equals S sub n. I'm not going to do anything to S sub n that would change the series in any way, except just make the first number be last and the last number be first. So we're going to write this a sub n plus a sub n minus D plus a sub n. Whoops, this should be 2D, my bad. Minus 2D plus dot dot dot. Now we're going to write these first three terms. A sub 1 plus 2d plus a sub 1 plus d plus a sub 1. Okay? Now I'm going to take these two series and I'm going to add them together, term by term. So I'm going to get a sub 1 plus a sub n. Well, first I need to add these two. So s sub n plus s sub n equals 2s sub n. And now I'm going to add the first two terms. A sub 1 plus a sub n. Now I'm going to add the second two terms. But look at this. The d's cancel. So I'm left with a sub 1 plus a sub n. And then, okay, so if I took these two sequences and added them up term by term, I would have an n number of a sub 1 plus a sub n. Then if I divide both sides by 2, then I'm left with s sub n is equal to n times a sub 1 plus a sub n divided by 2. So that's my general formula for an arithmetic series. All right, let's go back to our football player. So if I were to add up his 18 payments using plan A, he starts off with $10,000. That's my a sub 1 for 18 games. So his a sub n is $180,000. And then our n is 18 because that's how many games we're adding up. So if I took 18 times the first number plus the last number and divided by 2, I would get 1,710,000. And that's what we got when we added them up by hand. Where is it? Right here. Okay. All right, let's take a look now at a geometric series. Okay, so remember, a geometric series is when each succeeding term is being multiplied by some ratio. Okay, so our first term is a sub 1, and then our next term we're multiplying some r. Then our next term, we're multiplying by r again, so r squared. Then our next term is this term multiplied by r again, so r cubed. Okay, all the way down to the last term, which is a sub 1 times r to the n. So when I take this series, all right, and I'm going to go ahead and rewrite it down here. And then I multiplied each term of the series by r. So then I get a sub 1 times r, a sub 1 times r squared, a sub 1 r cubed, a sub 1 r to the fourth. So I just took each term and multiplied them by r. Now I'm going to take s sub n and subtract r times s sub n. If I do that, then these two cancel, 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 and the only thing I'm left with is a sub 1 plus a sub 1 times r to the nth power. So now I'm going to take s sub n and factor it out. So I'm left with s sub n times 1 minus r is equal, now I'm going to take a sub 1 and factor that out. A sub 1 times 1 plus r to the nth power. If I divide then both sides by 1 minus r, I'm left with s sub n is equal to a sub 1 times 1 plus r to the nth power, all divided by 1 minus r. And this is the general formula for a geometric series. In other words, this is the formula for taking the sum of n number of terms in a geometric sequence. Now, what if the sequence is infinite? Okay, so are you serious, sister? Is this possible? Think about it. You're on a football field, okay, and I have 10 yards to go to make a first down. Let's say instead of 4 tries to make 10 yards, I have an infinite number of tries. But the first down I get halfway. Second down I get halfway. Third down I get halfway. Fourth down I get halfway. And I get halfway all the way until the 10th yard line. Okay? This only works. Okay, so I actually can take the sum of an infinite geometric series only if my common ratio is a fraction. Okay, because if it's not a fraction, or if it's not less than 1, so if my absolute value of r is less than 1, then what's happening is then I have an infinite number of numbers and I can't add up an infinite geometric sequence. So the general formula for a geometric series, an infinite geometric series, is a sub 1 over 1 minus r. Again, that only works if r is a fraction, and then if it's not, then it's infinite.